Hello CIO world, and welcome to another installment of Chemical Engineering Design. In this lecture we will go over multiphase flow, and we will cover the different types of multiphase flows that one can come across in industry, as well as various aspects that need to be identified and considered when dealing with such flow systems. Of course, there are preferred flow systems depending on what you have, and just to be sure, make sure that you go over the information that is provided in the handbook, especially if there are some principles that you are not sure about. And also just make sure that you can tick off all the requirements for the study theme as shown here. Now, irrespective of the materials that can be used to make up multiphase flows, there will always be more or less four distinct types. There will be liquid-gas mixtures, there will be liquid-solid mixtures, gas-solid mixtures, as well as liquid-liquid mixtures. You will most definitely come across most, if not all, of these types of flows in your profession as a chemical engineer, unless you work at a bank. The first case of multiphase flow was introduced to you in thermodynamics, believe it or not, and mass transfer, and pertains to liquid-liquid flow. For such systems, we make use of the same design equations as before and take on average densities, viscosities, volumetric flow rates, and linear flow rates using the following relations, of course. And you plug these into the pressure drop, and you can then use the same equations as we have been using for piping system design. Now, in the case of vapor-liquid flows, I would definitely not like to be a fish or turtle. This type of system is characterized by various flow patterns, specifically bubbly, slug, churn, and annular, and also mist and other things, and well, some other various possibilities can arise, and these are dependent on whether the pipeline is horizontal or vertical, and what type of fluids you are working with. But regardless of this, it is possible to predict the flow patterns if the individual liquid and gas velocities are known. And these are easily determined through a mass balance. Some attempts have been made to plot such patterns as regions on a graph, such as this, all right? But just use this with caution, as there may obviously be deviations from the norm. Okay, so preferably just go to these equations instead of the graph. Where some flow patterns are acceptable, others may not be very acceptable at all. In the case of slug flow in particular, the design should always try to prevent this form from occurring. As slug flows, you can think of the inertia, banging into corners, etc. These types of flows are known to cause quite a lot of damage in pipes over time. Now, it is reasonable to have annular flow instead, so this is where the liquid is surrounding a gas, but there should be some contingency designed into the pipeline. And when I say that, I mean make sure that you still have some leeway in terms of flows. So annular flows should not transition into mist flow if there are dynamic disturbances which occur in the design flow rate. So you have a design flow rate like 50 meter cubed per hour, for example. If you were to shoot up to 75 meter cube per hour, you should still make sure that the design, the pipeline, will not cause a transition to occur to mist. So why this is the case is because it is really, really difficult to condense mists once they form. Okay, and this is especially difficult if you are working with non-polar organic solvents or, well, organic flows. So a good example of this is in my own research area of biofuel synthesis, where we work with pyrolysis oils. which form a type of mist when we try to condense them, and we typically have to make use of an electrostatic precipitator in order to condense the mist to form the oil. Otherwise, we just end up giving it back to the birds and the trees and the environment. So, how do we determine the pressure drops for such systems, for these two-phase systems made up of liquid and gases? Well, one option is to make use of the Lockhart Martinelli method, which was modified at a later stage. This is done by determining, firstly, the pressure drop associated to the liquid as if the liquid was not a two-phase flow. So if it was the sole liquid inside the pipeline. And we likewise do this for the gas flow as well. These two values then relate to the following correlation factors, which are represented by sigma squared. The square root of the ratio of the two-phase pressure drop contributions made by the liquid and by the gas together is defined as x. And by finding where the curves for the two sigma values, sigma L squared and sigma G squared, remember those correlations, we're talking about those sigma values, they are associated with these specific lines. You see the liquids going from the y-axis decreasing downwards, and the gas sigmas are going from near the origin, or not really, and then now moving up. This is a logarithmic plot, so just be aware of that. Okay, so once we know where these lines are located, where our values are placed on these lines, then we are able to determine a value for x. Okay, so you can calculate like x equal to 0.1 or 10 or whatever. It depends on the sigma values. Okay, and then it is possible to determine the two-phase pressure drop accordingly. I've not shown the specific method here. I've just summarized it for you in the lecture, but please be sure to go over this chapter in the textbook, as it explains it a lot better than I have. All right, and with this we end off our lecture on multiphase flow. Now, we haven't dealt with other flows like solid gas flows, solid liquid flows. I do have some information about that because we work a lot in my research area with solids, which are powders of biomass, which have to flow in gases, and there are some correlations that we use to determine how flow will proceed, but that's at the postgrad level. So this information is more or less what is required for you as chemical engineers, because you are typically only going to deal with these sorts of flows. And with that, we end off our lecture, and we will continue with chapter 8 and deal with other types of flow that you could experience. Okay.